code Brooks builds. What is it? This is the learning game design patterns. The GG Infinite Runner. And we'll open up code here. So right now we have the main library. When we create a tree, where does that happen again? We have updated. Okay, so here we have create tree. We're figuring out the timing of that. We're figuring out the arena width and height. And then we're just pushing, we're creating a new tree and pushing it, the result of that into this this vector of trees. And that's pretty much it. If I wanted to clone this, I could create a single tree. And right now, what is our options for this? If I run this, also I want to turn off the collision detection, which I think is that in player. Yeah, player running into obstacle. I can just not notify when that happens. I'd say they're not notify when it happens, or on the score side. No, not score side. That's the game state side on notify. So if we just say, you know what, I don't really care. I don't really care if we die. So cargo run. We have to run this in normal mode, because if we run this in release mode, it's like 2,000 frames per second and impossible to play. So the big, I think what we see here is it's the same size trunk, but potentially different sizes of the tree branches. And what I mean by that is the number of those green triangles on top is randomized for us. If I say that all trees have, I don't know, four of them. But then we go to maybe dealing with height, and we can now have like a randomly tall one. I think that might end up being good. We could then at the end, so we could create a tall tree and a small tree, and then use that copy method to like implement copy on it, or like have a clone method for it. Now, clone is something that's built into Rust. I can implement it myself, or I could just derive clone on it. So if I come to a tree, yeah, we're already deriving copy and clone on this tree. We could create some trees that are, I don't know, the correct, like whatever the right shape and size and everything else that we want for it. So when we give a new, we give it the arena height, arena width, the tree model, and the RNG. Okay, so this is, the RNG gives us the leaf count is RNG gen range. So what happens if I remove this? We just say, you know what? They're all 4. It's all 4. Which means that I might be able to put that into the tree model. I'm able to come down here and say, okay, the leaf count is 4. think this would need to be a U size if I want to use it in like the loop like that. So that will come now in a tree model. The location is still based upon the arena width and height. The branch color, we're trying to make that randomized, but we could potentially just make this, put this in a tree model as well. So branch color equals color I think I'd do from RGB, and then I can go, yeah, U8, so 0 through 255 now. So we can come back to here and search for, sort of like a green RGB. So if I chose something like this, well, that's hex color 0080, but I happen to know that Firefox here, I can, in Inspector, Eyedropper, just take that. Come back to here. Wait, no, that's not right. Can I not do that? Oh, it has to be RGB. Oh, sorry, it has to. It has to be hex. I want RGB. Oh, it has it right here. 01280. 01280. All right, so that's branch color. Also add in here. You are a color. Back to tree. So we are not going to need to store our branch color anymore. We don't really need our leaf count either here. Can we? Oh, I guess we do. Because the tree model. Oh no, we'll need to pass in the tree model every time we use it. And we don't really care about like storing those things. All we're really caring about right now is just this location. Everything else is the same across all the trees at this point in time. And so then in draw, so for tree count so instead of self.leaf count, this is now going to be tree model dot leaf count. That is private, so let's, I could either put a get, let's do the get. Okay, so self.leaf count. So what do you need? So this is going to be get leaf count. And branch color is also private. Here are a color. And we're going to not get leaf count, get the branch. You didn't find it? Pub function get branch color. Right, because you're self. I need you to be the tree model. And then I can do Get branch color. Okay, what's next? This function takes 3 arguments before we're supplied. Okay, so when we're creating a tree, all we care about now is the arena width and arena height and the tree model, and that's it. So we no longer need to pass in RNG. So save that. And the tree, everything should still be good, right? So if I do cargo run again, we should still be able to get trees. And they should also all have 4 branches. I'm waiting for another one to be created, but okay. That just happened to be that 25-second wait time, like maximum wait time for that. All right. So we've created the same exact tree. So if I wanted to implement clone on that, which clone already exists, so now I just need to make some kind of generator class for entities, and we're going to take in a tree. And when it takes in a tree, we're going to be able to call clone on it. And that's all we're going to do. So when we're going to, let's see, here in the main library, when we create the tree, instead of having to create the tree and pass in the arena width and arena height, we want to store maybe this tree inside of a self. So inside of the main game. And then we're going to want to push that, clone the tree, and then push it in. So if at the beginning here, if I say that I want to store a tree, so we're going to store a tree, and this is going to be type tree. So let's try this. Let tree equals tree new. All right, so we need the arena width. We need the arena height. Do we have those here? We do. We do have the arena width, arena height. So the arena width, the arena height, and a reference to the tree model, which we have here too. So tree model. This gives us a brand new tree that we can use, and we're just going to store that, stuff that in here. Now, we don't have to like add a method or anything to this. When we want to create a new tree, we have to figure out our timing stuff. That's still the same. We no longer need to get the arena width and arena height. Like those are all given, like those are all stored on that tree. So instead, we're going to push a self.tree.clone into trees here. I mean, it does make things a little bit simpler, but it also, as you notice, took away some of the uniqueness that we have with each of the trees. Like they all look exactly the same. Of course, it was mentioned that that's kind of like how games are. They don't want too many different things. So let's see if we get, okay, so we're still able to get the trees, and I want like at least one other one to show up. Okay, there. So we got 2 trees. They're exactly the same. Okay, so that's a good sign. Now, if I want to now make it so we can have another type of tree. So we did tall tree. So let's do that. We want a tall tree. A tall tree is going to share everything with the tree model. So we have a tall tree. Okay, so we still have the tree type. We still have the tree model, but we're gonna have to maybe for the height of the trunk, store that on a tree itself. So trunk height can be an F32, and we can take this in when we create a new tree. I don't know if I necessarily want to have a type in here where I say like, hey, give me the type, and then I would like pass that in to tree model. That might work for me passing in like, hey, this is my type. Give me all my stuff. So if I did something like, okay, I want type, and this is going to be a static stir. Oh, type is a keyword. This would have to be tree type. Okay, so we have so either we do that, or we take in the trunk height. I wonder if I don't store the trunk height, if I store the tree type, and we make this a static stir. We're gonna store the tree type in here. For the get the leaves length, we don't necessarily need to care about this, but the trunk height, we're definitely gonna want to pass in the tree type. And if possible, I could just reference to the tree type. That's for the arena height. So if we just do that straight off the bat, and so this is get the trunk height. That means everywhere else we're using this, which is nowhere else. That's interesting. Okay, so get the trunk height off of the tree model. Self trunk height. So we're now going to have a tree type, which is a static stir. I don't know if I can pass in a reference like that. Nope, I certainly can. So I'm passing a slice of a static string. Now this is just passing, the entirety of the trunk height. So now we can change this to say, well, we want trunk height, but maybe tall trunk height. And this is an F32. And so we have trunk height. If I copy you and we say that you are like 550, you're just 200 pixels taller. That's it. And you're also tall trunk height. Now in trunk height, we get the static stir. we can match on this this tree type. You know, instead of, we can have the compiler help us a little bit more if we use an enum here. So in tree model, in this same file even, I could probably have a pub enum tree type, and we could have normal and tall are the two types, as it were. Okay, so we have tree type coming in, and so we have these heights. We store those. Okay, so get trunk height, instead of, so tree type, instead of passing in this reference to a string, what if we passed in this a tree type? I mean, I could even do a reference to it. Now I'm going to need to match on that. So we're going to return a match on tree type, which means that we're going to have tree type. If you're normal, we're going to return self dot tree trunk height. Tree type. If you're tall, we are going to return tall trunk height. And that's it. So this get trunk height now works with both, and we're gonna just pass in what type are we getting. So if we walk backwards from this, back to the tree here, when we create new here, we have the tree type. This shouldn't be a static stir anymore. So here in library, let's actually use this. So in tree model, we also have the tree type, and that will allow us to now in tree here use super tree model and tree type. Tree type is now going to be this tree type here. So when we create the new tree type, you are going to be type tree type. So we've taken a tree type, which is this enum. Oh, we need to implement clone for the tree type enum. Right, because we're cloning and copying. So clone and copy. All right, so we have tree type, which is tree type. We're going to take in the tree type when we create the new tree, and then we are going to just store that. And we're not really going to care at that point in time. Now, when we draw, we need to get, oh no, right here. So get tree model, get trunk height, pass in a reference to the tree type. Okay, that seems to be fine right now. And then where's our other error for when we're calling this, I betty? So when we create the new tree, we're passing in this tree model. What we're not passing in is the fourth argument, which is the tree type. So let's add that in, which for right now, we'll just do a normal tree. So tree type, normal. No errors. Tree is happy. I think that everything should just work. We should be able to create trees all day long. All right, so we were able to create one, and then let's wait to make sure that the copy and clone. Okay, that works just fine. Now we want to make a tall tree. So in the main library, we have tree, which means we're also going to want a tall tree, which is type tree. Okay, so tree new, the arena width, the arena height, a reference to the tree model, and tree type tall. And we'll just store this down here, tall tree. So we've created two that are sort of like just basic, basic trees there. And when we create the tree, we need now, so we're gonna push a clone of one of these trees in. We now need to make the decision, which tree do we want to go with? So we can do an RNG here. So we can, I think we can do match. RNG, is there one that will like give us a true false? Or yeah, a true false is pretty much what we care about. Or like choosing something randomly from a vector would be really nice. So let's see, let's go to crates, let's go to I need you open. Rand. Oh, random generates a Boolean. Okay. What else can we do with this? Is there a like oh, there's a Rust Rand book. I guess if I want like a random like in a vector index. No, that's like from a random weights. What else? What else could we do? Array. Okay, uniform sampling by type for tuples and arrays. I mean, we could just have it be like store these in an array, like the tree types in arrays, or the clonable trees in an array. The standard and uniform distributions each support a selection of these types up to 12 tuples and 32 element arrays. This includes the empty tuple and array. Wait, they haven't. So it's a distribution trait. Sample iter. Wait, is that something I can call? I wish the documentation had a little bit more. So what is this? This is random distribution. So can I creates rand is right here. The most downloaded crate ever. So let's see. What is this? This is distribution. Used to create a random instance of T. It's possible to sample from a distribution.sample. Which produces an iterator that samples from the distribution. Okay, so here's just a maybe better example. Okay, so we have a vector. Uniform new inclusive 1 through 6. so we created a die range. So role is, okay, so die range dot sample iter, and then pass in RNG. And then that'll give us a random one that we got. Ooh, so roll die dot next dot unwrap. Okay, so we can do something like this. I think this will work. So I'm going to move this over into the other screen so they can watch that, reference that. Actually, I can do that on the screen. Okay, so coming back up to here, if we want instead of, these are both the same types. So I can do, they're never going to grow. So I should be able to do just an array of tree. That makes you so unhappy. Well, why does it make all of you unhappy too? It's just this one. Okay, so we want a tree and tall tree. Oh, and we want you to be trees. I guess it's not trees. We already have a trees, don't we? This is tree exemplars, like clonable trees. Trees to clone. So I'm going to call this trees to clone, and you are going to be an array of tree and tall tree. Okay, so if I save you, why are you all upset? Okay, so you're upset. Okay. The size for values of type tree cannot be known at compilation time. Doesn't have a size known at compilation time. Because there's some things about it that are on the heap, I think. So we should just store this on a vector. Or it should be a tuple or something. So let's just do a vector, a vec of tree. And so a vec of tree and tall tree. Okay, that makes everything a lot happier. Now we come down here, and so we have this trees. We have RNG that's just self.rng. I should be able to do let tree to clone, maybe even just tree. Let tree equals so it's die range. Oh, okay. We have to create this off of rand distributions uniform, and then we can create a sample of that later. So die range. I don't know what type that is. We'll find out when this fails for us. So down here, we're gonna need to use RNG or rand. So we have rand prelude. We also need rand distributions. Distributions uniform. This is probably gonna have to change. My guess is gonna be like a uniform type, but we'll find that out. So let trees to clone equals, it's gonna be our uniform new inclusive. Oh, that's it. Just low and high. I want... Okay, so then they have alphanumeric, standard, distribution, alphanumeric, uniform, standard. Okay, so uniform doesn't look like what I need. Alphanumeric probably is not what I need. We have standard and distribution left. Where did that go? Here. So we have distribution. Like, can I give it a type and then it figures that out? Oh, that's off of this. That's just the trait that gives a sample iter. So it's not going to be distribution. I wonder if standard. If not, I'll just do the thing where I just get a number, the index randomized. It would be nice if we can just do this. This can be standard. I guess standard is a little bit weird. Let's just do, if I don't have this here, so rand distribution standard. We'll go rand distributions standard new. You don't seem to be giving me any help here. No function. Oh, okay. So standard isn't something I can call directly either. All right. Well, implementation on for and types distribution T. Okay. So what about this uniform? Can I? A distribution uniformly sampling numbers within a given range. I guess I could make a uniform based upon the length of the vector that's inclusive, I think. So new inclusive can sample integers. So that's how I can figure out how many there are. Extending uniform to support a custom type. Write a backend which implements the uniform sampler trait, then implement the sample uniform helper trait to register your backend. Okay, so they have a uniform for F32s and inner uniform float. So they implement uniform sampler for this custom struct. Okay, so they have two structures. They have a struct my F32, which is a tuple that stores an F32. They have new B1 and B2, low B1, high B2. Where B1 is a sample borrow, which comes from rand, self x, so self this type, plus sized. I don't know if I'm going to do this with trees because they're not sized. That's just for like custom number types. I think like the best I would be able to do is abstract it away into a tree chooser or something like that, which I don't necessarily think is super helpful with this. So I don't think we're going to be able to go with this way. I think what we're going to do is just have a vector of a tree and tall tree to begin with. Just make trees to clone like you. We'll come back down here and we'll have to create our random index. So let tree index, maybe just index, equals self.rng.genRange. We're going to want this to be between 0 and I can't remember, is it inclusive? It doesn't say here. Vrizix, hello, good morning. Maybe you can create a distribution of these indexes instead of the real type. I can do that. Yeah. Yeah, that's actually a really good idea. And they would all be the right type too of numbers. So we can go back to uniform. So let's go back to, so we have rand prelude. So use rand distributions uniform. I bet I need to pull in all those other ones to use them, because you need to pull them in for the. I mean, I guess it's also a good question. Does prelude? What does prelude bring in? I wonder if it's bringing it in for me. Well, it'll yell at me if I'm bringing it in already. Okay, so we have the trees to clone. We're also going to need to store the distribution of trees to clone. So trees to clone distribution, which we know is a type uniform. So this is trees to clone distribution. And this is going to be a uniform new inclusive. Our low is 0, and our high is going to be trees to clone dot length -1, because it's inclusive. And that's it. So then we're going to store the trees to clone distribution down here. Okay, so that. What are you? Sample. Oh, I need to give it the type, don't I? Sample uniform. So if I give it a usize, that makes you happy. Right. We don't need to do this genRange anymore. So in uniform, here we have this new with that. We can sample. Okay, so we can sample the side, and that gives us a random point. Okay, so tree, self-trees put. So we need to know which of the trees we're going to want to push to clone up. So self.trees to push. Let's give ourselves the random. So let index equals. It looks like it's going to be self trees to clone distribution dot sample self.rng. Oh, the opposite. I can do RNG dot. Okay, let's try that. RNG dot sample. And then this can be self dot trees to clone distribution. You don't seem to be happy with that. Cannot find. Oh, right, because you're self.rng. Now you're cloning. Can I give you a reference? Yeah, okay. That's a good sign so far. So index, you're a usize. So now tree, self.trees to push, self.tree.clone. So now we're going to say self.trees to clone of position index dot clone. I don't need to do anything with that. We're just going to push straight into trees. And that's it. Save you, and let's see if you work. That is a tall tree. So the first one's a tall tree. Second one's a tall tree. I'm waiting to see if we can get a normal size tree or if they're literally all going to be tall trees. Which would be a little bit unfortunate. Or if I make a lot of them. So I think up here we're storing where's that number? Let's see. Create tree. Oh, from the random gen range of like 1 to 30. If I do like 1 to 1, so every 1 second, I'm gonna do every 1 to 2. Okay, there we go. So now we're getting tall trees and non-tall trees. Okay, so that's a super good sign. Now we're gonna want to actually make the tall trees have taller trunks. Right now they're not taller for real, or like they're not drawing taller. When we draw the tree, the tree model, so right, okay, so we're doing the leaf count here. We're drawing all the leaves. So we draw the leaves mesh however many times we need to. Where are we drawing the trunk? Because I see, okay, so oh, here it is. Graphics draw, context, tree model, get trunk mesh, and then the location is self.location.x, self.location.y. So get trunk mesh. So we now need 2 trunk meshes. So on tree model, we have a trunk mesh, and then we're also going to need a tall trunk mesh. So here's this this trunk mesh. Let's just copy this and create a new one. So tall trunk mesh. It's a rectangle. It should be exactly the same, except the height is going to be different. So we have trunk height here. This is going to be tall trunk height. And then tall trunk mesh. Which means that now we can get the trunk mesh. We're going to need to get the tree type. which is a reference to tree type. Now we're going to match on tree type if it is tree type normal. Then we're going to return self dot, I guess it's going to be a reference to self dot trunk mesh. What do we have mesh wise? Trunk mesh. Otherwise, if it's tree type tall, a reference to self dot tall trunk mesh. Okay. Nope, that was correct. Okay, so that's everything here. Now back to tree. You're upset because we need to get trunk mesh. I need to pass in a reference to self dot tree type. Does that make it just work for us? Let's find out. Okay, yeah, so now we see these tall trees that are showing up here. So that's perfect. And if I want the tall trees to be drawn, I mean, I guess it doesn't matter too much if they're drawn like before or behind. But if I want them to be drawn behind, I need to put them at the beginning of the vector of trees. And let's see what docs, standard library. I want to go to vector. Is there, so I know there's a push. Is there a like an insert at? Or can I like insert at the beginning? Because here's push, appends an element to the back of the connection, the collection. Is there like front? There's only 2 matches for front. Rotate left and rotate right. Rotates the slice in place such that the first self.length minus k elements of the slice move to the end, while the last k elements move to the front. Is there like another insert here? I mean, so we have append. Moves all of the elements of other into self, leaving other empty. Because that's not what I want. Insert. Inserts an element a position index within a vector, shifting all elements after it to the right. So I can insert at position 0. Everything else should be rotated to the right, and we shouldn't lose any trees. I think that's how that works. So if when we create our tree model, so this is in the main library here, we're going to create a tree. We're going to need to know what kind of tree it is. We don't necessarily know off of this. So instead of just like blindly passing in, let's just get let tree equals. We're going to get a clone of the tree here. We're not going to, but well, we might insert, or we might push. I think we're gonna have to match on the tree type. So inside of tree, I can either lens this, or I can just like pub the tree type. So if I pub the tree type, then I can match off of tree dot tree type. Yep, normal and tall is not covered. Okay, so then we have tree type normal. If it's normal, we're going to push it to the back of the vector. So we're going to say self dot trees dot push tree. However, if it's tree type tall, we're going to self dot trees dot insert. The index is 0, so at the beginning, and the element is going to be tree. And so that should guarantee that they'll show up at the back. Now, because they're all the exact same color of branches, that's not the best, like the best possible thing here. We might be able to do something with the mesh where we have like just a basic outline of the trees. We can make some other kind of background with this. I think the next thing to do to match up with what we have with the P5 JavaScript game, we want to make it so that the trees that are tall are farther away from us and they're moving slower. In the tree model, we have the speed, right? The velocity, that's this. So if we do the exact same thing here, if we have velocity and tall velocity, so this will be a vector 2 f32. So here's our velocity. So you will be now a tall velocity, vector 2. So instead of negative 0.5, if I do negative 0.1, so slow it down significantly, maybe like 0.2, so a little bit more than half. Our tall velocity here, and then when we have get velocity, we will take in a tree type, which is a reference to a tree type. We will now match on tree type. If you are not like that, tree type like that. So if you are a tree type normal, then we're going to return a reference to self.velocity. If you are a tree type tall, we're going to return a reference to self.tall velocity. And that's it for that. Now we just follow the errors. So takes one element, so we're going to pass in a reference to self.tree type. And we're going to run, and hopefully tall trees now move slower and sort of look a little bit farther away. Yeah, and we can definitely see that. Now we can see as we're entering into the forest here, and so there's this really dense forest, farther away from us. And then we have the closer forest that's that we're actually moving through. But this looks appropriate. Now we're slowing our frames per second down significantly because we're creating so many trees. Let's fix that by putting in the main library, we were just creating a tree every 1 second, essentially. If we bring this back to maybe something like every 10, up to 10 seconds, we might. Maybe even 15. No, 30 was maybe too long. there's a tall tree. And here is a smaller tree as it comes along. And so we can see us as we sort of like we're just strolling through this forest. Everything's fine. You know, just by itself like that, we get a little bit of depth for this. So that actually looks pretty cool. Renan, good morning. You like the taller tree effects? It's not even like that much. We just slowed them down, and we just get this for free. So it's, I guess it's something to sort of, I mean, like keep in mind that this is something that we can add to games that add in a little just. It just makes things look so much better, just for free. I know, parallax, a simple parallax. And there might be things we can do, like make the taller ones a little bit darker. But I think that for the example, what I'm trying to go for here, which is showing off the this code, specifically the prototype pattern, I think is the important thing here. And smaller scale too. Oh, well, I was having them be, let's see. I could have the front ones be smaller. The back ones, I don't know if I actually want them to be like that much smaller. There is this scale that could be done, but for right now, we'll just stick with this. Okay, so to recap, for the prototype, the pattern, what we ended up doing was we came into the tree model and we added in, the tree model is now aware of tall trees and normal trees. To that end, we've declared an enum of tall and normal. And in the tree model itself, it's now keeping track of, well, this is what it means to be a tall tree. And this is what it means to be a, like the speed. This is the tall trees have this speed. Tall trees have this velocity. What's really cool about this is I have a lens to you just give me the trunk mesh, for example. The caller doesn't necessarily care that, we don't need two methods for this now, for like get tall mesh, get short, get normal mesh. We pass in the tree type, which is, reference to that enum, and then we match and return, hey, if you're the normal one, here you get this mesh. Otherwise, you get this other mesh. So we've abstracted away the complexity of choosing which type of tree you're of, all to this tree model, and that's it. Yeah, I know farther away is smaller, but at the same time, if it's small, I mean, if it's smaller, I guess we could have the tall trees in front and the shorter trees in back. Like, I guess that kind of makes sense. To continue on, then all that in the main library, we end up creating two trees. We create a normal tree and a tall tree, just one instance of them, and we add them to a vector of trees to clone. So these are trees that are just sort of sitting out there and not moving. So if we could somehow move the camera over and see them, that's they would just be sitting there. And I think they're not being rendered because they're not a member of the trees vector, which is what's being rendered. When we go to create the tree, we create, well, we also have this like sample, so we're doing some like RNG fun, but basically we just figure out, hey, which tree do we want to create that tree, specifically clone that tree, and then decide, well, hey, based upon your type, do we want to put you at the front of the array of tree or the vector of trees or the back of the vector of trees? And that's just a clever way of making it so that the tall trees get drawn first and the shorter trees get drawn second. We could easily reverse this around by having this be an insert. like that, and this being a push like that. And that just completely makes it the opposite. Besides that, all trees needs to do is just be handed its type and pass that type in when it makes sense to the tree model when it's getting all the information for it. And that's how we can, with a minimal of extra work, now have multiple tree types and implement that. So that's pretty cool. Oh, we should probably have like the opposite speed too, because that's a little bit weird to have the small trees that are farther away moving faster. So yeah, we want to also switch around the velocity. This could be -2, and this is 0.5, like that. Physics. Amethyst has a kind of prototype implementation where they read model.ron files into the game. I was thinking about that because I've heard about RON files of Rust object notation, sort of a play on JSON, JavaScript object notation. But I wasn't sure. I wasn't completely sure how I would like potentially do the what we did with JavaScript, where we extend and we say, okay, well, here's like the base tree, and then here's like the prototype, and now grab this other thing and then add in data that doesn't exist on like the base tree. Because I know like everything is typed. So I might look into Ron, but I'm not. I don't know if like the way I was wanting to use it works completely in this sense. All right. Well, with that, it is over my time, so I've got to go get ready to go to work. Anyways, thank you everybody for stopping by and watching. I'm really happy that we were able to get this working. It makes the game look so much better just by this one tiny little change. So I hope that you're able to understand the prototype pattern, when to use it, when not to use it, and then also like go implementing that to the game, or just learn and do whatever you feel like. I am doing these specific streams for the learning the game programming stuff on the patterns, game programming patterns, on Mondays through Fridays, 7 a.m. to 8:15 or so Mountain Time. But I don't have any other scheduled streams. If I do those, you can follow me here on Twitch or Twitter, and then you'll get notifications of when I do go live. But with that, I hope that you have a great rest of your day, a great weekend, and I'll see you at the next stream.